Hello, and welcome back to another coding session with Mr. Jacob. Today, we want to combine the learnings from the last sessions with our PixelLoop rendering engine thingy that we created. The one, for example, that we used to create the sand simulation. I will have linked all the videos about the PixelLoop engine and the sand simulation in the description, and you will have about here a link to this latest sand simulation video if you would like to take a look at that. But in today's session, I want to actually integrate a console renderer into our PixelLoop engine. As you can see, I've recreated this simple example of the bouncing box in the PixelLoop engine. We will shortly go over the code that is doing exactly that stuff here in a rendering window, which you can see here, which is created by the pixels backed WGPU thingy here and rendered to the screen. But what I want to do is actually, I want to render all that stuff into my terminal here in exactly the same way we did in the last video. You will have that linked here somewhere up there as well. We will use Unicode characters and ANSI colors to actually render out whatever we are doing in the PixelLoop engine into the terminal. Effectively, this of course only works if we have a quite low amount of pixels we are rendering. So we need to have the proper space in the terminal, of course. But let's see if we can actually achieve that, and I hope that this will actually go quite quickly. So let's jump into the editor here and let's take a look at what I did. I have created this trivial CLI demo example as a starting point for us. First of all, because I haven't worked in my own PixelLoop engine for quite some time and needed to familiarize myself with it again. And on the other side, that we have something to start with to work on when now implementing this CLI renderer part from scratch and not being in the need of creating this simple demo, which on the other hand only has 84 lines of code, so it's not that dramatic. Let's take a quick look at what we are actually doing here to create this bouncing rectangle there, because that's actually quite easy. First of all, we have a PixelLoop game state, which first of all has the position of our box. It has the current moving velocity actually of the box, so in which direction and where is it moving, with what speed and so on. And we have a size of our box. And as you can see, we are initializing this here with the position, which is simply a default, so the position will be 0, 0. The box direction, which is the velocity, it is moving into the right direction and down, because our starting point is top left, our 0, 0 point. And it is moving with a speed of 1, because as you have seen already, it's fast enough that way. And we will give it a size of 10 by 10 pixels. We could, for example, change that to like something like, something like 20 by 20 pixels. And actually, I'm not quite sure why my task switcher is on the wrong screen, but yeah, we'll see. And now it should be, more lengthy in size. Maybe we can keep it that way. Yeah, why not? Okay, so this is the box size. And now to the main application we are using here. We are actually creating a canvas of a size of 80 by 60 pixels. For our pixel display engine here, we are scaling this up by times of 8, because otherwise we would have this really small window here with the moving rectangle, and I don't think you can see this quite okay, and neither can I actually. So I kind of scaled this up here, and this is what I'm creating here. I'm creating two contexts. I'm creating first of all our window using our PixelLoop and WInit implementation to create the PixelLoop window, which I'm actually scaling by our system here. And then I'm creating our currently used pixels canvas, which is the WGPU hardware-backed frame buffer canvas thingy that we are currently using in our implementation. Again, if you want to learn more about that and what we are doing there, I have linked one of the corresponding videos in the description and in the upper right corner there. We are then initializing our state object here for our PixelLoop to hold that, just printing out some debug information about what we are actually rendering, and then we are running our PixelLoop. Our PixelLoop system gets the state, some context, the canvas itself, and then an update function, which is this one here. We will take a look at that in a second, and a render function. And that is essentially all the magic. Don't think too much about this one. That's actually something that I need to refactor in the future. That is a kind of a window state update function. Again, if you want to know more about that specifically, take a look at one of the other videos. But what's important is we have these update cycles which occur 60 times a second every time, and it is made sure that this is correctly synced with our rendering frame. So even if we have a slower rendering time, the updates occur and are synced so that we don't have different speeds and stuff like that. So in this function, we are actually moving the box along. So we are only moving it. We are not drawing it. We are only moving it. Using PixelLoop is always a two-state process. So we are always having this update loop, and then we have the render loop, which in turn, renders the world, while the update loop updates all the things in the world. And this is essentially what we are doing here. We are getting from our state the position and the current direction, as well as the box size. We are then moving our box into the corresponding directions and simply checking if it has collided with one of the walls at one of the 4 walls of the display. And if it is so, we are simply rotating the velocity into the other direction. So if it's collided on the right side, we are moving it to the left. If it's collided on the bottom, we are moving it then further on the to the top, and so on. So we are simply inverting the velocity, so to make it bounce, and we are ensuring that it's never out of the screen by then applying this new velocity to it to move it along in the direction. We are then updating our state to the corresponding new data we have created here, so the new position and the new direction, and that's it. That's it for our updates. And then when we do the rendering, which is the rendering function here, we are simply using a yellow color. I could change that, but you have seen that it's a nice and bright yellow. We can see that without a problem. Then we are clearing the screen to a black color here. And then we are telling our canvas to draw a filled rect at the position X and Y of our box with the size, with the width and height of our box, and use this color yellow. And in the end then, when we have finished all our drawing commands, which is kind of a queue of drawing commands there, we call our canvas and say to it, it should be please render out. And that's everything. That's our full demo. It's not nothing magically, it's nothing special. It's simply using our PixelLoop system to achieve this in, what have I said, 84 lines of code, which is quite nice actually. What we now want to do is we want to be able to use the same drawing code we have here and simply write a new output driver, you could say, for our PixelLoop engine, which then results in rendering all that stuff to the terminal instead of to a window which is hardware accelerated and backed by something. I'm not discussing here if this is if this is an intelligent thing to do or if it's the right thing to do. I just want to play around with it, and we will see. Maybe this is slow as hell, but then we have the opportunity to actually optimize it in another session maybe and take a look at that. Or maybe it's just fun. I'm just doing this with you together for fun, and I hope you have fun as well. And as I'm currently playing around with the terminal and liking it, I'm doing that. So how do this renderers work? How do we do that? We have a concept of a so-called canvas in our PixelLoop. So let's take a look at our PixelLoop library and let's see where the canvas trait actually lives. There is the canvas trait. And the canvas trait actually, it implements quite some nice functionality like this rec drawing and stuff like that. Like, for example, you have seen the clear screen and filled rect and whatnot ever. Functions are implemented on a canvas. But what's the most interesting thing about a canvas is that it's a trait we can implement. And it's a trait which essentially needs you to implement those 4 functions. A function which tells you its width, a function which tells you its height, which can set a range of colors, which can get a range of colors from the canvas, and that's it. And we need to implement that actually for our CLI or maybe cross-term canvas, however we want to call that one. And then once we have done this, which is quite a simple logic to do, we will take a look at how to implement the rendering, because there is a specific other trait, I've splitted that actually, which is renderable canvas or something like that. Because a canvas is only something that can actually, that can hold information for you. It could be a plain in-memory canvas holding a picture for you, which you want to then render out somewhere or move around somewhere or something like that. But what we want to do is we want a renderable canvas. This is actually the thing that you can use as an entry point, as a primary canvas to our engine, which can then be used to render it out. And essentially those are the functions that we need to implement for a renderable canvas. But we will see in a second what that actually means. So let's start with a new canvas implementation. And maybe we can call it, where is actually this trivial CLI demo? And let's, oh no, that's the wrong folder. Actually, I want it in PixelLoop because it's living in the main engine part. So yeah, let's maybe just call it cross-term canvas. Why not? So cross-term canvas RS. Okay. First of all, we need to go back once more to our, no, that was the wrong one, the trivial CLI demo. And we need to, no, not the trivial CLI demo. I'm sorry. We need to go to the main library of the PixelLoop, and we need to publicly include the mod then there, which is called cross-term canvas now. And then we can go back to our cross-term canvas, and now we can actually start. So I guess what we want here is a pub struct, which we call cross-term canvas. I guess we first need something like a width, which is, I think, a U16 in cross-term, if I remember correctly from the last time. And we need a height, but I'm not sure, maybe. Yeah, let's first go on here. Those may be the wrong data types because our trait has a width and a height function and it returns something. I guess it is a U32 or something like that. Maybe we should store that in the U32, but I don't really care at the moment. So we have this one, and we will definitely need some sort of a pixel buffer. So what we want here is a vector of colors, actually, of our PixelLoop color implementation, which we actually have and can use here. So let's use this one. And then I guess what we want is a simple new function here. So pubfn new, which takes a width and a height. And maybe initialization color, but I'm not sure. I guess we will simply initialize the buffer black or something like that. So let's return that, which would be width, height, and we want a buffer, and this buffer would be a vector of colors from RGB, simply 0, 0, 0. And we want width times height elements in there, and I guess we need those as usize, because otherwise it won't work. Okay, so we now should be able to create our canvas here, and now let's implement canvas for cross-term canvas. And let's first import the canvas, and then let's have it give us all the missing members, which would be the width. And there it is. We need to return a U32, but in the end, we can easily convert a U16 to a U32 because there can't be an overlap in this conversion direction, so an overflow. So this shouldn't be a problem there. So let's just do width as U32, and here we can do self height as U32, and then we need to set a range in our buffer. So how could we do that? Self buffer. So essentially we get a range which should be set, and we get an array of colors which we should set there. So we can simply say we want this range, and we want copy from slice, and this should actually work, I guess. So essentially what we are doing here is we are taking the specific range that is requested from our buffer array, and we are copying, essentially mem copying the data we got into this buffer slice. And that's essentially what we want to do here. And if we want to get the range, we should simply be able to return the range here. And it wants a reference to it. So yeah, so there we are simply returning data. As we are creating our own in-memory buffer here, which is of the same data structure, the color here, the color that we are actually setting and getting, it's really easy for us to implement this methods here because we are using the same data structure. If we would now implement that on the basis of something else, like example the pixel scrape, which we did before, then we need to convert the information around and stuff like that. But we don't need to do that here because we are specifying this for ourselves. So now we actually have a valid canvas implementation which we can use to store data, pixel data in memory. But what we essentially really want to do is we want to implement a renderable canvas. So let's implement renderable canvas for cross-term canvas. And let's import the renderable canvas, and let's have it give us the members to implement. We need the render function. We will do that in a second because that's essentially what we need to render the pixel data which is in the canvas to the terminal. Then we need something which converts a physical position to a canvas position. That's actually something if you click somewhere, but I need to refactor the PixelLoop engine for that a little bit more because it doesn't yet support a generalized event handling system for mouse clicks and stuff like that. So I guess we will not implement that here. But we might in the future, because it is essentially possible to get mouse clicks in the terminal and then give it to the system so that we could react to that and render based on that, which would really be a really nice thing. We could then implement something in the terminal using PixelLoop, which would be great. We need to implement something like resize surface and resize. This is again the thing that we had before, but the difference between the display layer and the underlying data layer, which we had before when I had this 8x scaling there. That is the difference between surface and not the surface, but the real system. I will refactor that in the future, and for now I'm not 100% sure that I want to be able to resize the terminal. So let's go ahead and do the minimal stuff so that we can actually render our simple animation here into the terminal, which would be to implement the render function. Okay, so let's think about how we would actually do that. Essentially, we would do that mostly in the same way as we did in our session before. We are using half block Unicode characters. So we are actually using half block Unicode, something like that. I never know the character specifically, but I always copy it out of the Wikipedia. No, what did I do? Copy link to? No, I didn't want to copy a link to highlight anything. What I actually want to do is have this const, what was it called? Upper half block. So Unicode upper half block, which would be a string, I think. So, and then, yeah, and then we would have this character in there, and the string, of course, would be static. Even though I think it could have resolved that actually, and we need to return an OK here just to have it shut up about the error. And this upper half block is actually a line which is cut in two, and the upper part of it is shown. So what we can do with that, just to reiterate on that, if you haven't seen the last video, which I link there, is that we can actually split every row into two and therefore create kind of the illusion of having square pixels in a console. Because as you can see here in this editor, if you see this cursor blinking, the text characters always have double height in comparison to their width. So we don't have square pixels, and that makes things, of course, a little bit hard. But if we can use this, we can actually double the vertical resolution by splitting the pixels in half and then using the foreground color for the upper one and the background color of the pixels for the lower one. And this actually works out quite nice, as we have seen the last time. So we can actually do something like that. And yeah, I actually want to do something like that. But first of all, I need to install the cross-term dependency, because I don't think that it is currently in this project, because I've not needed it here yet. So let's install cross-term into our PixelLoop dependencies. So now we have cross-term here. And now I should actually be able to import, what is it? Use cross-term. There is something like, yeah, queuable command. And I need something else. I need access to stdout, but we can actually maybe import this directly. Would be a little bit more readable. So we want to print our data to stdout. So let's first of all get a handle to the stdout writer by taking stdout, std, io, stdout. Yeah, there we are. So, or was it something like, I guess it was something like that. Yeah. So the other thing was the type, I guess. So now we should have a handle to stdout, and we should actually be able to print something to it. And using cross-term, we can easily print all this kind of ANSI characters and control characters to move the cursor around and to add color to it, or to do all kinds of different stuff there. And we will actually do that. We need to iterate through our pixel data, of course, and we need to iterate line by line, of course, because we somehow need to print it line by line. We can move around in the terminal randomly, but this is not very fast. It is quite slow. So we want to do it line by line. So as the cursor moves, we are going with it. So we need to iterate for y. It would be 0 to self.height. But our height is a double from what we actually have in lines of the terminal. So as I've said before, we have these lines and we have pixels, and the pixels have double the height because we have double the vertical resolution. We want to use with one of those half upper block characters to essentially print it out. So what we need to do is we need to step through our pixel height, because our canvas height is our pixel height, by 2, because we are only printing each second row, so to speak. And then we need to do an iteration over x, which would be 0 to self width. And there we don't need to do anything really special, because the width of the character, as you can see, if you take a look at something like this here, a character is the width is the right spacing. So we are essentially using it in the same way. Okay, so now that we have done that, we actually need to think about how we want to render this. And we want to render this in a way that we now need 2 pixels. We need the upper part of the pixels from our data storage or buffer and the lower part. So yeah. So let's maybe extract them from our data buffer. So let's call this one y1, which is the first one. It would be self.buffer. And as always, when we index into a linear array, which is kind of the pixel data of each row just after one another, we can easily calculate the index by taking the row, multiplying it with the width, so to speak, to get the length of how many rows we need to go along, and then simply adding x. And this is of course not working because width is, I think, a U16 and we need a U size or something like that. I'm not 100% sure what actually is this in the end as a... It is a U16. So, and this is a U16 as well. So where's the problem? The type color cannot be... Oh, yeah, that's the problem. We have all these U16s here, but what we actually need to do is we need to have it as a U size. So I'm not 100% sure. I think I want to calculate this here as a U size and this here as well, to convert it like that, and then convert this width as U size as well, in contrast to calculating this in a U16 space and then multiplying, then converting it to a U size, because maybe we would leave precision there on the table, and then, but I don't think that we actually would leave the U16 data space while being in a terminal, but you never know. So let's see. No, this should actually be no problem if we had done it in another way, because we are calculating this by using the U16 sizes. Okay. Okay, but now we have our y1 pixel, and now we need our y2 pixel, but we have to think about something there. The y2 pixel is always the second one, but if we have an odd rows, if we have an odd row count, we don't have this y2 here. So what we actually want to, because the second half of the pixel would simply be empty. So what we want to do is here, we want to take, we want to create an if condition here, which simply asks the if self height. And I'm not sure if there was something like is odd or something like that. Is that a possibility? I guess. I think there was something like that. No. Let's quickly Google that, because there is a function. We can of course use the modulo operator and stuff like that, but I want to do it the Rust way. So I think there was something like that. Yeah, is odd. Okay, there is a is odd create. Okay, we are doing it with with modulo. So if self height modulo 2 is not 0, then this thing actually is odd. So in this case, we simply return something like color new, color from RGB, and we are returning a black color here. Maybe we will find something more eligible, usable there in the future, but for now, let's do this. And otherwise, we can actually more or less take this here and put this in here. However, we need to add 1 to the y because we want to move 1 y further down. So what's the problem here now? Maybe it's missing semicolon, but there seems to be something else wrong there. What's the problem? So expected because of, or wait, what? What is he? If and else have incompatible types. Okay, what is this one returning? It's returning our color struct. That's fine for me. So this is not, oh yeah, this is not because I have a semicolon there. And now it should work. Okay, so now we have 2 properly filled up XY, Y1 and Y2 color spaces. So color values. So what we now need to do is we want to output the color configuration and this character here then for those 2 colors. So what we actually now need to do is we are using our std_out and we are queuing up a cross-term command. And we are queuing up the cross-term command called setColors. Yes, setColors. I remembered correctly from the last time. And setColors we need to, of course, import. And now it takes, if I remember correctly, a colors struct or something like that. Mismatched types. Oh, yeah, I need to put that there. And yeah, exactly. We need to put colors in there. So let's do that. Let's put colors in there. And there was a new constructor there. And let's maybe prefix this with style and import that because I don't want to confuse this with a color from our colors here, which would be kind of bad. Cannot mutate immutable variable std_out. Yeah, let's quickly fix that so that the red squiggles don't make me crazy there. So now we need to create new colors, and we create new colors by giving the system a foreground color and a background color. So yeah, let's do that. The foreground color is the upper one and the background color is the lower one because our character here has a filled part on the top and a non-filled part on the bottom. So let's do that. Colors, style, color, and there was RGB. Yes, there was. So let's do that. The R would be y1.r. The G would be y1.g. And the B would be y1.b. And now we need kind of the same thing here for the second line. However, we need this one replaced by a, yeah, what did I do there? The one replaced by a 2. And now we need to put a comma there because it's still a problem. Let's format this. And now we should have actually set those colors. So after having set those colors, we need to std_out queue the Unicode character because until now we haven't printed anything visible to the screen. We have only set the color for the next printed characters, so to speak. So let's quickly set the output the characters here. There is a print thingy here. Yeah, exactly. A print thingy here in crossterm, which we can use to Unicode to print this Unicode upper half block. Okay, so now we have that. And now we actually are ready for printing our lines of pixels, 2 at a time, always on top of each other. But now, of course, once we are finished with printing a line, we need to go into the next line. So what we need to do outside of this X loop here is we need to do something like std_out q print \n. So we want to go to the next, to the next line. But another thing that we learned the last time quite painfully was that If the canvas for some reason is not the full width of our terminal, then we have set a background color, for example, it will continue on all of the lines after that. So we have kind of color bleeding into the right side of the terminal. We don't want that. So at the end of each of our lines, we can simply cue reset colors. And this is, as you can see, this is really nice way of using cross-term, because it will use the correct ANSI sequences that the different systems understand and so on. And you don't need to remember strange escape codes like escape something something 23M semicolon something something. Those are really bad and weird escape codes, which you all normally can't remember. You always have some lookup tables somewhere which make it easier. So essentially this comes with cross-term, which is quite nice. Okay, so we are more or less ready. We can print all of this out. But one thing we need to still do, we need to move the cursor to the same position every time we want to print our canvas, because this is one screen, but this is called over and over and over again. And we don't want to print into the terminal and then print below it again and print below it again, but we want to move the cursor again to the position there. And I guess first we can simply do something like, which should work. I haven't not tried this yet, but there was something like move to cursor or something like that. Yeah, cross-term cursor, and there is a move to. Yeah, so let's do move to 0, 0, which should actually be the top left position in our terminal. So once you call that, you will get a movement to the top left, and then everything that has been there will be overwritten. Okay, and once we are finished with our frame, completely finished, I guess we should std out flush. Because we want to make sure that after each frame has been printed, we want to empty all our buffers and have it printed on the terminal screen. And why is this not working? Not found, std out. Okay, I guess we need to import stdio. Right? Do we need to import the write trait for that? Is that part of flush? Yeah, flush is part of the std write trait, so we need to import that in order to make it work. Furthermore, but we will see that in a second. It might be that we see the cursor flickering around while drawing it, but we can then handle that by hiding it. We had that in the matrix thingy we made. I will link that there as well. The matrix scroller in a terminal, the Matrix screen from the movie The Matrix, you might know it, where we had some flickering there, and we can easily hide the cursor there. So actually, what we've done now should be enough, maybe, to go ahead and try. Should we try? I guess we should try. So let's go back to our trivial CLI demo. And let's now remove the winit stuff here, and let's create a canvas here. Canvas equals cross-term canvas, I guess. And we needed to put the width and the height in there, and we have a width and the height here, 80 by 60. And yeah, we will see. Maybe we will change that in a second to actually ask cross-term to give us the screen size. But if we have the terminal in the right size, I might need to change the zoom level in a second. It should actually work, because I could now do width as U16 and the height as U16 here, and now we should actually, not yet, because we need to import our cross-term canvas. There we have it. And now I don't use the winit thingy here, but I use our usual run method, which doesn't have this strange window updating function here and state updating thingy. And then we put our canvas, our cross-term canvas into there. And what's the problem here now? Result. Okay, yeah, that makes kind of sense. I need to have a question mark there. And essentially, and as you have seen, did not change our render code. We are still using the same render functions and the same update functions. And I really hope this works. Let's see. Should we see? Let's see. So before we had, wait, let me show you without recompiling. Target release. No, target debug trivial CLI demo. This was the last, oh yeah, it was the small one. The last one that we tried out. But as you can see, it creates a window and it runs our animation. And if I now actually recompile it and tell the system to run it, let's cross our fingers. Maybe this works first try. I would love to have it work first try. Let's see. Compile. Please compile and please work. This would be awesome. We will see. It compiles. Yeah, it needs to compile all of that WGPU stuff in there and so on. I may change that and make it optional then in the future now that we have multiple output renderers. Or maybe we have multiple. Yes, that's awesome. We have that. That is actually my shell. That is my terminal. Okay, that's great. But as I've said, you can see all this flickering. That is actually the cursor jumping around and drawing our lines. So let me end this, and as you can see that it's still there. Let's fix this cursor thingy here. So, ladies and gentlemen, we have officially implemented an output driver for our PixelLoop engine for the terminal. I love that. Okay, so let's fix that because there is an ANSI escape sequence which can actually be used stdout.q to hide the cursor. So it should be possible to, is there a cursor hide? Yeah, there is a cursor hide. So it should be possible to hide the cursor, and we want to essentially, after each frame, we want to queue a cursor show command, maybe again, yeah. Because once you press, you are going out of it, you want the cursor back. So maybe we need some sort of system in the end which handles if you press Ctrl+C, so that it resets your terminal to a sane state. But for now, this should be enough. Okay, let's see. And as you can see, the flickering is gone. And this thing is actually moving quite smoothly. I like that. That's awesome. That's absolutely awesome. Okay, so let's see what happens if I make my terminal a lot smaller. Oh, it's staying the same size, of course. It's staying the same size, of course, because we have coded this. We have kind of hard coded this. Yeah, but there now, as you can see, there now happens something which I meant. My cursor is gone now because I've stopped it in the middle of a frame. I can of course fix that by it's not resets, it's reset, but yeah, I can call a reset, of course, which will get it back into a sane state. But yeah, we will need to do that, but we will do it in the future. Let's take a look if we can't. Where's our trivial CLI demo there? Maybe let's not use a fixed width and height there. So let's maybe remove this, but use crossterm to get the current terminal height to use the maximum space we can actually use. That would be nice, I guess, for this demo. So yeah, so maybe we can, how would we do that actually? We would do something like terminal width, terminal height, and this would be crossterm terminal size or something like that. Yeah. I remembered correctly, but I don't want to prefix this with cross term, but let's import the terminal thingy here. Okay, so, but this is not correct. This is not our width and our height. So what we want is actually, it is our width. So maybe our width is equal to our terminal height. And then I think we don't need this as U16 here anymore. But our height is not our terminal height. Our height is the double of our terminal height. So it's terminal height times 2, because we have actually doubled the vertical resolution by using those half block characters. So that's something we need to take into account. And now this actually might already work. Let's see if this. Okay, this did not work because I did something stupid, I guess. But it has at least the full height, I guess. But what did I do here wrong? Yeah, you were all screaming, I guess. I put the height into the width data. So let's see. Okay, this actually works, but it is kind of janky because maybe it's not fast enough to update that. Oh, I see something here. I see a flickering something here below, and I guess I know why. And that's most likely why it's so janky as well. We are always printing a new line after having rendered a line. And we do that even in case it's the last line. So once we have reached the end of our terminal space and we are finished, we are still going into the next line. And this, of course, is wrong. We should not do that if we are in our last line, because then the whole thing will be moved up by the terminal because someone pressed enter. So we are actually, for each frame, we are actually kind of scrolling up one line. And that's most likely what's causing the flickering and the stuttering there. Let's see. So we only want to go into the next line if we are not in the last line. So if y is, let's think about this. We have y, which is stepped by 2. So y will never be the last thingy there. Yeah, so what we actually want to do is we want to check y plus 1. If y plus 1 is bigger or equal to, no, if y plus 1 is smaller than self.height, then we want to go into the next line. And I guess I need to do as usize here. Then we want to print the new line, and otherwise we don't want to. And let me comment this. Don't print new line after last line. So let's see actually if this changes anything. It's still doing this stuttering here. I don't know if you can see this in the recording, but the thing is still kind of janky. And if I scroll up, I should, yeah, there you can actually see I'm now scrolling up. Those are all the, yeah, there. Those are all the lines that have been moved up. But what's actually wrong then with my thinking about this? Let me quickly think. I think the problem is that this thingy here is our y is 0 indexed. So what we actually want to do is here we want to subtract 1 from the height here. Yeah, maybe we want to do it like that. Okay, so let's see. And as you can see, we don't have any flickering anymore, and we have a nice black border around it, and it's just nice. It's actually, this is really, really, really smooth. I wouldn't have thought that. Okay, so now let's see. What if we make the terminal smaller? Okay, then we can see if we make it a lot smaller that we are not doing the most optimal way of drawing, because every time we are drawing everything. And yeah, maybe we can optimize that actually, but this would be something for another video. Okay, let's go to my normal terminal size. And in my normal terminal size, what I usually have if I'm not recording, this is actually really smooth. I wouldn't have thought that. Yeah, it's a little bit stuttery, but that might be because I'm screen recording at the same time. Are we actually executing? No, we are not. Let's rebuild this in release mode. Maybe this makes a difference as well. But mostly I think that the reason for it stuttering a little bit and getting slower is that the terminal isn't fast enough rendering all those characters out. But we will see. We will see. It's really, I love that. I really love that. That's absolutely awesome. We have written an output driver. Yeah, as I've thought, it's a terminal thingy. It's not a computational thingy there. But it's just awesome. Awesome. I can now, let's do something quickly. Let's maybe add, let's give this box a shadow. Yeah, let's do that. Let's give this box a simple shadow. So what we then need to do is we need to draw another box based on this one by using something like a darker yellow. So dark yellow. So maybe we have all of those values here. So let's do that quickly. And then let's draw this one first so that the otherwise will overlap with it. Let's give it a position which is offset by 1 pixel in both directions. And yeah, and this should already do the trick. Let's see. Do we have a, yeah, we have a shadow there. I don't know if you can see that. Maybe we need to give it more space there. Like, let's do 2 pixels. Yeah, now you can see that it has a shadow. We have essentially created a rendering engine for a terminal. Yeah, we could now maybe try and port our sand engine, our sand falling engine to the terminal. Maybe I will do that. Maybe I will do that in the future. I don't know yet, but I definitely will work further on this sometime. I don't know if the next one or whenever, but I will definitely work further on this. I love it. So yeah, if you are still there, thank you for following along again. Thank you for having this fun experiment with me. Please give me a thumbs up if you liked the video. Subscribe to my channel. Leave me a comment. All those things help me a lot because the YouTube algorithm then presents this video to more people which might like it as well as you do. So thank you again for staying with me and all the support you're already giving me and conversing with me about different topics. And I hope you enjoyed this one, and I hope to see you in the next one. So bye.